Okay, in the last video we talked a little more in detail about how delta S works. We need to introduce a concept called delta G, which is Gibbs free energy, and this is going to be used to determine whether or not a reaction is spontaneous. I am in this video going to try to derive delta G for you a little bit, and we'll kind of see how this works. Okay? So the backstory that we've seen up to this point is that one of the laws of thermodynamics is that for all spontaneous processes, the delta G of the universe has to be positive. So let me write that out. Delta S of the universe has to be positive. The entropy of the universe for every reaction has to be positive. Well, we just saw a reaction in the last video where it came out negative. Does this mean this reaction won't happen? Well, it turns out that delta S of the reaction is not the full story. So we're gonna derive an equation here, okay? The final answer is pretty easy to use actually, but for right now we're gonna have to deal with getting there. So we're gonna kind of simplify a few things here, okay? So it turns out, because obviously measuring delta S of the universe is basically impossible, but we're gonna need to approximate this if at all possible. So for this, we're gonna assume that delta H is the heat exchanged at constant pressure. Okay? And we've already said that delta S is the Q, and it's got to be reversible at constant temperature. Okay, so if we assume that we are at constant temperature and constant pressure, which in lab conditions is not really that uncommon, it turns out that we can simplify a few things. Okay. The delta S of the surroundings, meaning, if you've got a beaker full of reaction going on, everything that isn't in that reaction, or everything that isn't in that beaker, can be summarized as the delta H of the system divided by the temperature. Okay, you have to trust me that that is true. But the idea is that basically the heat being lost to the surroundings should be the only impact on the surroundings itself. Okay, so we can write that the delta S of the universe, right, because we said that heat lost at constant temperature is the heat, or it is delta S. Well, the delta S of the surroundings can be measured as how much heat is lost by delta H, so that's why it's negative. Okay. So the delta S of the universe can be summarized as the delta S of the system, whatever is in the beaker, minus delta H of the surroundings. So basically, the delta S of the universe is the delta S of the system plus the delta S of the surroundings. But we just summarized that as delta S of the system divided by T. Both of these are in terms of the system, which makes our life a little easier. So, some algebra here. I'm going to multiply everything on both sides by negative T. For right now, it's going to seem really weird that I'm doing that. Okay, and what we end up with is negative T delta S of the universe equals negative delta T S of the system, and this will cancel out to give us delta H of the system. This will become positive, so I'm just going to write that one first. Delta H of the system minus T delta S of the system. So the entire delta S of the universe can be measured in terms of things that we can measure in the system. And it turns out that negative T delta S of the universe is how we define delta G. Okay? And what this really means is we said way up here that the delta S of the universe has to be positive. Well, since now we've got negative T delta S of the universe, the negative sign means that we need this thing to be negative for it to be spontaneous, but these are all in terms of things that we can measure inside of a beaker. Okay, So we can determine spontaneity, basically whether a reaction is spontaneous. Can't spell, sorry. In terms of the system only. In terms of the system. Which is super useful because it's really difficult to measure the delta S of the universe. But measuring things, basically measuring everything that's in the beaker, makes life a whole lot easier. So let me try to summarize some of this at the bottom here. Hopefully I don't run out of space. So, Gibbs free energy is delta G. Okay. And the simplified equation for this, everything can be in terms of the system. We can just remove the word system here. Delta G is inherently negative T delta S of the universe, which is what we need to determine spontaneity. We can simplify it as delta G equals delta H minus T delta S. This simplifies things a lot. As much as all of this looked kind of horrifying and the prospect of having to determine the delta S of the universe, this isn't too bad. Here's the outcome of this. It turns out that delta S is important for determining spontaneity, but also delta H. Obviously, if you've got a reaction that has too much of an energy barrier, like if it requires too much energy, the reaction won't happen. Both of these are important, and depending on the reaction, one can override the other, but they're both important. But delta G is the end-all be-all as to whether or not things are spontaneous. We said that delta S of the universe has to be positive, and delta G is negative T times delta S of the universe. So since this needs to be positive, and we're taking a negative sign in front, we need delta G to be negative. So if delta G is negative, the reaction is spontaneous. If delta G is positive, this means it's non-spontaneous. This doesn't mean the reaction can't happen, it just means we're gonna have to pump energy in, or electricity, or we're gonna have to put some effort into it. If delta G equals 0, we are at equilibrium. Which means if we ever get to delta G equals 0, all of the stuff we learned in the equilibrium chapter is relevant again. Okay? So, let's try an example where we use this equation. Okay. So, in a previous problem, in the previous video, we saw this example. 4HCl gas plus O2 gas forms 2Cl2 of gas plus 2H2O gas. Everything is a gas in this example. Okay. Well, the delta H of this could be measured. You know, you basically just run the reaction and see how much heat comes out. And somebody has measured this, and it's at standard conditions, it's negative 114.4 kilojoules per mole. In the previous video, we took the time to use the Appendix C data, which I didn't really wade through all of this, but the concept was there. So if you look back at the previous video or the notes, delta S for this exact reaction was found to be negative 128.8 joules per mole Kelvin. Okay. We want to know, based off delta G and delta S, what is delta G at standard conditions? So in other words, at 298 Kelvin. 25 degrees Celsius is 298 Kelvin. Okay. Well, delta G equals delta H minus T delta S. Okay. Well, we have all these things. We just got to make sure the units cancel out. So, delta H we just got was negative 114.4. That looks encouraging because we like delta G to be negative. That means it's spontaneous. That's literally the thing we summarized at the bottom of the last page. If delta G is negative, this reaction is spontaneous. Minus T, which is 298 Kelvin, and delta S was 128.8 joules per mole. This is kilojoules. Okay, either way, and this is joules. We need one of these two to be changed. I'm going to convert this to kilojoules, which means I divide by 1,000, so this is negative 0.1288. Kilojoules per mole Kelvin. Okay, so our K's cancel out, and we get kilojoules per mole and kilojoules per mole. The negatives are going to cancel out and we get a positive value. So essentially what we would do is we would get 114.4, I guess I'll actually type this in for you, negative 114.4 plus, because the two negatives cancel out, 298 times 0.1288. And I got negative 76.0, basically. So delta G, at standard conditions, I guess, because everything else was the standard conditions, comes out to negative 76.0 kilojoules per mole, which tells us that this reaction should be spontaneous at these conditions. Okay. Right, so we got our answer. Yay. Okay. What this also points out, if you look at this equation, is that delta H does not matter what temperature it is. Okay, this is just the difference between the reactants and products in terms of stability. It turns out that entropy does very, very much so depend on temperature. So if we had increased the temperature a lot, so if we weren't doing this at standard conditions, if we had done this at really high temperatures, so as we did this at like 500 degrees, this is going to start having more of an impact on whether or not the reaction is going to be spontaneous. So this is kind of a general trend, is that delta S is going to have more of an impact at higher temperatures than at lower temperatures. So, if you're really, really low temperatures, like you're near absolute zero, you can almost ignore entropy. But if you're at really, really high temperatures, like suppose you're like, I don't know, looking at reactions on the surface of the sun or something, and the temperatures are, thousands and thousands and millions of degrees or whatever, you can almost ignore delta H. At typical room temperatures or reasonable temperatures in a lab setting, both are going to be important because, they both have an impact on this. Okay? Couple other odds and ends here. It turns out that you can also measure delta G by taking products minus reactants of, you just look up all the compounds and look up the delta G values and take products minus reactants. It's exactly the same concept. Similarly, it also works for Hess's law. So delta G, Hess's law is still true. So all the stuff that we could do with delta H with Hess's law still works. You can also use appendix C. So it kind of just depends on what information you're given and how you're solving it. Like on this one, we had delta H and we had already solved for delta S, so we used those in the equation to solve for delta G. If you had just been given this and asked what is delta G and you had the table of data, you would just look up each of the individual things and take products minus reactants like we did for delta S, or like we have done in previous chapters for delta H. Okay, so it's super consistent, it works either way, and you should get the same answer. But, all right, thank you guys.